Okay. Our lesson that we're going to incorporate into what we already do with our students is over convection currents. Robert Salazar, Lea Naranjo, and we are with Memorial Middle School, and we both teach 8th grade science. The presenter information that we felt most went along with what we wanted to incorporate was the presentation that Anna gave us. Again, you all should remember it about the helmet and things like that. So we felt she was geared more toward what we want to teach. Our lesson overview is going to take approximately about 4 days. So we're going to do something each day within that time frame. And it's also going to be a cross-curriculum involving the 8th grade math classes. Our content focus, the students should be able to make qualitative observations about each of the following. And this is regarding the behavior of objects with different densities in water. That is on day 1. Gas properties, a little bit about the Charles' Law on day 2. Convection currents in water systems, and it is a closed water system. And then also convection currents and how they function in hot air balloons. Continuing with their content focus, students should be able to collect quantitative data about the following: an object's mass and volume, and that's where we get into the cross-curriculum with our math classes, and then also about the dimensions of the hot air balloon. Student prereqs. They should already know how to calculate mass using a digital scale. Obviously, it's fairly simple. Program it to the units that you want it to, whether it's to the hundredths or to the thousandths. Place, y'all should know this already. This is where we're going to do the cross-curriculum. They're going to calculate the volume of certain objects in their math classes, and then they'll bring back that information so we can complete the lesson in science. Also, measuring length accurately using a ruler. Learning objectives. Students will be able to make qualitative observations of objects with different densities in water and also keep an accurate data log.
Okay, so the activity we have planned for this one, of course, we're going to get 3 objects, preferably soda cans closed, and get them with different masses regarding their sugar content. And then what they'll be able to do is they'll see that they all have the same volume, but they all have a different mass because of the sugar content. And what we're going to do is we're going to have a setup with an aquarium. And I thought I put it in there. Did you move it? Okay. This aquarium, basically, we can break it into a grid so they're able to see it, stuff like that. And then with each different soda can, they'll be able to drop it in. And based on the sugar content, it should probably it should fall in one of these quadrants here, and they'll see the different densities based on they have the same volume but a different mass. And then a follow-up to that would be getting 3 different size water bottles. We'd have maybe the pint size, this normal size, and the larger one, and putting the same mass, let's say 50 grams of sand in every water bottle. It's the same mass but a different volume. And then, of course, going to the aquarium and doing the same thing, and they can kind of see the relationship with mass and volume and how that applies to density. Like Karen said, it's a derivative. Mass they can see, volume they can see, but density, it's derived from both of those together. And hopefully this activity would allow them to do that. Activity sheets for this kind of have a setup, almost like a basic lab setup where they have some tables, they collect data, make predictions, then answer a few questions pertaining to the data they collected in terms of the soda can and also the water bottle. So let's look back to this. Yeah, like just varying sugar content and getting those things in there, so they're able to actually see how that affects them. So basically, with density, they'll apply to convection currents. Basically, all these lessons are going to do with convection currents. There's a lot of dynamics in there, so we're breaking each little component in there so they're able to better visualize it because it's convection current. How do you see that? And if we break it up, it'll be a little easier for them to actually see every single component of that. For day 2, using a simulation, going to the FET website, we found one over balloons and buoyancy, and I'll show you that in just a second. And what they'll do is they'll follow a worksheet. Which was it? This one? Okay. And basically, it has some instructions for them to do. They'll manipulate the simulation as we go along. And ultimately what will end up happening is as they manipulate it step by step, they'll see different properties. Again, kind of like the same principle with the aquarium. As you manipulate stuff, what happens to it. And they'll get, a better understanding. They can pump in some molecules in here. And then, of course, there's some instruction that go along with that. And they'll see what happens. And then maybe they'll change the conditions, like add some heat to the system or cool it down. And again, they'll see how the molecules behave with that. And so they get a better visualization of what actually happened in a convection current. So they'll be using a simulation, following a guide that we've created step by step. And then, of course, answering questions and trying to draw conclusions based on what they're seeing in the actual simulation with the molecules and stuff like that. So we've got density, we've got how molecules behave. For the third day, okay. We're going to use the water system so they can actually see this in action. They'll make qualitative observations about a behavior of water in a closed system. And this will be their setup in their science notebook, where they'll draw. Basically, what we usually do with this is we have. Where's it? Here it is. This is our setup. We have two tubes. They're connected together by two other tubes, and we can add water into this system. We usually change the temperature on both sides. We add colored dye to it, and they can see the dye actually separates depending on what it's doing. They can see it in action, and this is their setup. As we go along with this, they make hypotheses. We don't do any talking. We do very little talking. It's more about showing them what's going on, and so they can formulate their thoughts in their heads, and they're able to, hopefully, at the very end with a summary, conclude what they saw and maybe understand. After knowing how molecules behave, knowing a little bit more about density, they get a better understanding of that.
Was that a foldable?
No, it's in their notebook. Oh. Yeah. Okay, so after they see it in action, that's all the same thing, right? Mm-hmm. Okay. Day 4 is they're going to utilize what they've learned so far and apply that to a hot air balloon. Of course, now we're dealing with air, and of course they'll use the engineering process to construct a balloon. What we use for this is we have birthday candles, some straws, and a trash bag, and that's all we give them. And we'll give them some tape. And using that, they apply what they're doing and the whole engineering process, what they know about convection currents, molecules and density and stuff like that. And ultimately, the idea is to get their balloons to fly. And there's a couple of trial and error things with that. Do you have a picture of that?
Yes.
Last year when we did it, we really didn't extend it as much as we are with this lesson plan. But I'd show you this to kids that they got some other things done, some of them stood to the top of the cafeteria and stuff like that. But now what we did here is just incorporate more models and more simulations to kind of help them get a better understanding. And last year was just more like we built it flies, and now we can hopefully translate that back to Earth system. So yeah, so what we did, we broke all the components down, and then for our teaks, it says they're supposed to know how convection currents power Earth systems like the weather, the ocean currents, and climatic interactions. So now they know the mechanics of it, they can hopefully translate it and apply it when they actually see a model of the Earth system, or maybe the ocean currents or climatic interactions as well. That was the idea with that.
Can you not do that outside because of the wind?
No, we do.
Okay, I just didn't know because it's been so windy here.
No, last year we kept it in the cafeteria. I actually went on my own and took a couple of guys. I just wanted to see how high they would go. Yeah. And I was telling Joe about it, and it just flew off. Yeah. And it was like that big, and it probably went over the King Ranch. And I was like, no, I don't think we should have done it. They probably sort of grass fire or something. And it got out of sight, and we never saw it again. And it got up pretty high. Yeah.
Yeah. We did it on the football field usually.
And of course, before we have them, construct their blueprints and what have you, we just show them simple videos on how these hot air balloons are constructed. Now, it's not using the same materials. Again, we give them specific materials. They're not allowed to bring anything from home just because that wouldn't be fair to everybody else. And so this gives them an idea of how to create it, and then they go back and sketch their blueprint, and that's where they have to, determine the length of the straws, how many candles should I put in order for my balloon to lift off, things like that. And so this is just a quick little video here.
Can't do that here.
Everything.
So go to Indiana.
So here they're using the balsa wood. We try and incorporate something that we have access to, so straws would be easier for us to use, cheaper as well. So when they're actually designing and building their hot air balloon, they have to figure out through trial and error, were my candles too long? Did I burn my trash bag? What do I have to do to adjust it to make my hot air balloon take off?
So they don't see this before?
No.
Okay.
Yeah, basically this that model I showed you, like this is like the basic pattern.
Yeah.
Go and
Don't have that.
yeah. What some of them did, some of them would cut the bag because they thought it'd heat up quicker, and the bag just melted completely, and that was it. Like I said, like ultimately, like we've broken down all the components of it, and then hopefully got a better understanding of how it works, and then applying it to like a bigger diagram, like something in the Earth system, or maybe ocean currents. You know, they can explain that, or even tectonic plates. We'll talk a little bit about that. They can know how tectonic plates move and stuff like that, and hopefully they get the mechanics down. And like you said with Anna's presentation, talking about the helmet design, you know, and maybe the gas molecules, the different densities of the molecules in them as well. You know, once they know the mechanics of convection curves, you know, they can apply it in any other setting as well.
Yeah, I would think you guys could think about and tie into the oil spill here. I mean, everything went the other way, you guys were spared, but that whole thing was based on the ocean currents, and certainly gonna, well, it has just had this devastating impact commercially and, you know, economically. There could be so many tie-ins, but, you know, there's your real world current thing. You've seen an experiment too with a big pie plate where you put Kool-Aid in it and then sand and then you drip water on it, and the kids predict the plume that the Kool-Aid will make. And if you use a glass pie plate, all you have to do is lift it up when you're done and see what it is. I'll send that to you because it's not intuitive. They will guess incorrectly about the plume and what the underground water plumes do. I'll send that as well. Questions or ideas or anything spark some thoughts in your heads? Hard to ask at 3 o'clock on Friday. Good job, guys. Thank you.
Thanks.